And we'll begin this panel on black holes. First of all, I'm supposed to announce on behalf of the management that there is a misprint in your program and that both the silent auction and the out loud auction are ending tonight. So that means if you want to bid on any of the weird, wonderful, and unique items that we have on auction, today is the time to do it. You can't do it tomorrow.
By 7:30, I think.
By 7:30 tonight. The other thing I wanted to ask while we have a moment, how people heard about SETIcon. How many of you were in SETIcon 1? So we have a lot of repeat offenders. How many of you heard about this because you got an email from the SETI Institute? How many of you heard about this from the media? Heard about this on the radio, newspapers, etc.? How many of you heard about it from a friend? An enemy? Okay. And so for how many of you is this your first SETI Institute event that you've ever attended?
Wow, that's
great. Excellent. I'm so glad to see that. All right, so we have, as you have gathered by now, made a real attempt on the program committee to put together programs that have a diversity of views and backgrounds, and we certainly have a wonderful example of that here today. We're going to be talking with both scientists and science fiction writers about one of my favorite topics in astronomy, black holes. So let me introduce the panel, and then we will have each of the panel members make a short opening statement. We'll have a little bit of discussion among the panel members, and then we'll open it up for your questions and personal odysseys about black holes. So beginning on my right, your left, Alex Filippenko is one of the world's most highly cited astronomers, not by the police, but by his colleagues. He was a member of both teams that used observations of exploding stars to discover the accelerating expansion of the universe, a discovery which was honored with the 2011 Nobel Prize in Physics to the team leaders. Alex has been voted the best professor on the UC Berkeley campus a record 9 times, and he was selected as National Professor of the Year in 2006. So Alex Filippenko on my right. All right. Rob Sawyer on his right is a Canadian science fiction writer who has published almost 20 novels and lots of short fiction. And if I may embarrass him, he is, I think, the most skilled interpreter of SETI ideas in science fiction. Nobody writes about SETI as well as Rob has. He has won 44 national and international awards for his fiction, most prominently the Nebula Award, which is the highest award given by the science fiction writers themselves to their colleagues. His books have appeared on top 10 lists, have been made into films and television shows, and we're delighted to have Rob Sawyer with us. Leonard Mladenov is a professor of physics at Caltech and a noted popularizer of science. He is co-author with Stephen Hawking of the very well-reviewed book, The Grand Design, and has written a number of other books about science as well. In addition, Leonard has written for several television series, including Star Trek, The Next Generation. So he is in both the worlds of science and science fiction. Leonard. And then, last but not least, Andre Bormanis is an American television producer, screenwriter, science advisor, and author. He is the author of the book Star Trek, Science Logs, and he's uniquely qualified to write a book like that because, and I'm very jealous, he was the science consultant on the following Star Trek series: Star Trek The Next Generation, Star Trek Deep Space Nine, Star Trek Voyager, and Star Trek Enterprise. So here to live long and prosper is Andre Bormanis. And I'm Andrew Fracknoy. I am the Vice Chair of the Board of Trustees here at the SETI Institute. I teach astronomy at neighboring Foothill College, and I have the pleasure of acting as moderator. So we've asked each panelist to begin our discussion of black holes from their unique perspective, and as I say, then we'll have lots of time for you to participate. Let's start with Alex Filippenko.
Right, so I'll just tell you a little bit about how we find black holes or black hole candidates. You can't see black holes directly because nothing, not even light, can escape. That's sort of a definition of a black hole. But we can tell that a black hole is present based on its effect on its surroundings. So suppose you have a black hole and another star orbiting their common center of mass in a binary system. The black hole used to be a massive star, but at the end of its life, it collapsed. Well, if you measure the orbital parameters of the visible star, in particular, its orbital period and the speed with which it's orbiting, and that you can do through a series of spectra, then you can use those two parameters to figure out the mass, the minimum mass, it turns out, of the object that's causing that visible star to orbit. It's initially a minimum mass because you don't know the inclination of the orbital plane toward your line of sight. If that minimum mass exceeds 3 times the mass of the sun, and you can't see an object there, then it's pretty likely a black hole, because we don't know of any normal stars or even dim stars that could have a mass exceeding 3 times the mass of the sun yet still be invisible. Okay, a normal star would have a huge luminosity if it were more than 3 times the mass of the sun, and white dwarfs and neutron stars, a dim form of star, can't be that massive. All right. So that's the so-called stellar mass black holes, and then we try to find other evidence that there really is a black hole there, like if material is being swallowed, then it kind of becomes dimmer and dimmer, whereas if it's hitting the surface of a neutron star, then it actually glows brightly when it hits the surface, because when you drop things and they hit surfaces, they heat up. So you can look for other evidence that way. Those are the stellar mass black holes, and there's quite good evidence for them in our own galaxy. Several dozen of them have been found. Then there's the supermassive black holes that exist at the center of nearly every big galaxy. Our own Milky Way has one having a mass of about 4 million times the mass of the sun, and that's pretty small on the range of supermassive black holes. And it's detected in the same way. You actually track the motions of stars over a couple of decades, and this has been done by at least 2 groups of astronomers who get these very, very clear pictures of the center of our galaxy using various techniques to minimize the turbulence in our own atmosphere, or at least the effects that it has on the pictures. And they can just track the motions of these stars and figure out from their orbits that there's this dark thing 4 million times the mass of the sun pulling on them. And that's actually, in my opinion, the very best evidence for a black hole. It's the one in the middle of our galaxy. And people say, well, you haven't yet proved that it's a black hole, and that's true, but any other object that we can think of is a much more radical explanation. In other words, the black hole is the conservative explanation for the data that astronomers have gathered, certainly in the case of the object in the middle of our galaxy, and in a few other galaxies, and in the case of stellar mass black holes. So I think black holes almost certainly exist. I'm willing to bet my house on them. That's not a very tough bet because I rent, and so it's no big deal if I, But, I'm not, quite yet willing to bet my life on them because it's conceivable that there's some kind of an intermediate state of matter that's very dense but not quite yet a black hole. But I doubt it. I think that the discovery of black holes is now at least 99% certain. And there you go.
So I thought we would do the scientists first and then the science fiction writers. So I'm going to let Leonard.
The sublime to the ridiculous.
Yeah. Leonard.
Maybe I'm a good transition person then. So I'll try to supplement that with a little bit about the history of our concept of the black hole. And the first person to think about such things was a guy named John Michel in the 1700s. And he reasoned using just classical Newton's laws which is that, you know, if you throw something up, it comes down, right? That's one of Newton's laws, as people say, the law of gravity. But people knew that if you throw something up faster, it'll go higher before it comes down, and that if you throw it up fast enough, it won't ever come down. It'll have enough energy to escape the Earth. And this is called the escape velocity. And he reasoned that if escape velocity was the speed of light, then light would not be able to escape something that was massive enough. So that thing could be captured. But of course, at that time, nobody thought or knew how, you know, they didn't really understand light very well, and they didn't know that, realize that light would be attracted by gravity, but they thought it was a possibility. And then after Einstein came up with his theory of general relativity, which shows that light is affected by gravity, a few months later, a fellow named Schwarzschild came up with a solution of Einstein's equations, which shows what happens when you have a ball of matter, and solve the equations for general relativity, showing what the dynamics of things are if you have if just one ball of matter in the universe. And that solution shows that if the ball of matter is dense enough, has enough matter in it, that at some point you'll have what you call the event horizon, and that things that go past that will never come out again, because gravity bends the paths of things, and it'll bend it enough that the path of all things just goes right back to the center. But again, nobody really understood that at that time, or what it meant, until the 1930s, when a few people took this further, like the great Indian physicist Chandrasekhar and J. Robert Oppenheimer started to consider whether these might be real objects. But still, when I was a kid in the 60s, people didn't really take black holes or neutron stars very seriously. They thought they were perhaps just mathematical anomalies or interesting things in the equations, but they maybe didn't really exist. And when I guess I was about 15, about 69, I think, I remember reading about this very excitedly in Scientific American, something called pulsars, which were then explained as being neutron stars that are rotating. And suddenly people started realizing these things might exist. And then in the early 70s, the first candidates for black holes were identified. And then, of course, Stephen Hawking's work really took it, and Roger Penrose a step farther, and suddenly it became a hot topic. And the idea of cosmology and black holes was not only something of a curiosity, but a hot topic in physics. And the idea of how a black hole forms is that when you have a star, it's like Schwarzschild considered. It's a big ball of mass. But you might, since matter all attracts other matter, you would think, why does it have a size? Why doesn't it just collapse? Because everything is attracting everything else. But the thing is that when this big ball of mass if it starts to get smaller, it heats up and it puts things under high pressure and heat, and it forms nuclear fusion, which forms heat, which tends to expand it, and there's a delicate balance that's going on. And when a star ages and that fusion process starts to taper off, then gravity wins and the star can collapse, and then eventually it can form a black hole or a neutron star. So that's a brief history of black holes and how we've learned about them.
Great. Rob.
This panel topic is unique amongst the panel topics in your program book. All the other panel topics actually suggest what we should be talking about. They say, are robots or humans better for space exploration? Discuss. How will you survive a trip to Mars? Discuss. This is simply a noun. The black hole, heart of darkness. So without any particular direction to take the discussion in, I just want to say I'm for them. Science fiction, of course, I like to call the distant early warning system for science popularization. We grab the stuff as soon as it's out there and start playing with it. So there have been good science fictional treatments of neutron stars since 1960s, black holes certainly since 1970s. I know my friend Andre is going to talk to you about the uses of black holes in the Star Trek universe, so I'm not going to touch on that, but I am going to touch on what I think is the best science fiction novel ever written, my own personal favorite, and it's by a guy named Frederik Pohl. Frederik with no C in it, and Pohl, P-O-H-L, which is a great word to pop your microphone with, Pohl. Frederik Pohl's novel is called Gateway. It came out in 1976, I believe. If I'm not right, it's 77. And Gateway is about a mission well, it's kind of funny. I'll get parenthetically to this. The central sorting facility for Canada Post, the mail service where I live, is called Gateway. And the thing about Gateway is you send a letter into it, and it might go where you intended it to go, or it might go somewhere else, or it might just disappear. And I actually told Fred this some years ago, and he said, well, I'm going to tell everybody now that that's the origin of Gateway, the asteroid in his novel, where there are alien spaceships left behind, and you get on board one, and you might be able to pilot it to where you think you want it to go, or it might go somewhere else, or it might just disappear, literally is what happens. And the story deals with Robinette Broadhead, who is a character who is the only survivor of a mission to a black hole. They never intended to go there, but when their ship came out of hyperspace, there it was, right near the event horizon of a black hole. And it was a ship kind of, the geometry doesn't really matter, but it's a notion of kind of the command service module, lunar module pairing that we're used to from the Apollo missions, a spaceship that has two components. And it's right there on the threshold of the black hole. And in order to save himself, our guy kicks himself out of the black hole, which has the effect of kicking everybody else into the black hole, And what happens when you get into one of these areas of super high mass? One of the things that happens is that your perception of time passing, of course it seems normal for you, it seems like everything has slowed down in the external universe a great deal, and the converse is true. So the problem is this guy has done a horrific thing. He has abandoned all his friends, and no matter how many decades of therapy he goes through for having abandoned his friends to save himself, because of the physics of a black hole, his friends are always at that incredibly attenuated moment where they realize that they're betrayed. And the use of the physics of a black hole to get to this incredibly human emotion that nobody has ever experienced before. No matter what horrible thing I do to Leonard right now, 10 years from now we'll meet at another conference and we'll laugh about it. I remember that time you gave me a wedgie in front of everybody at SETIcon. Wasn't that funny? And I said, well, I'm over it now, Rob, but if I would have killed you at the time.
I did get over the last time you did it.
That's right, exactly. But this is, I think, what draws science fiction writers to black holes. Sure, they're neat to write about in terms of cool things they do in terms of gravitational lensing and all that. That's all description. But I think what Fred Pohl did brilliantly was find a way to turn the black hole, the astronomical phenomenon, into something that absolutely spoke to the human heart, to a very dark part of the human part, which maybe brings us to our title, Black Holes, Heart of Darkness. And I'm going to turn it over to my friend. Well,
No, that's fine. Andre.
Andy, turn it over to Andre.
Thank you.
Oh, thank you.
Thank you. Yeah, that's a nice segue, Rob. Dealing with cutting-edge ideas from physics, from astronomy, the other sciences was something that we were certainly eager to do on the various incarnations of Star Trek that I worked on. The writers were always asking me for, is there some cool phenomenon that has been discovered recently that we haven't seen on an episode before? The 500 and some odd episodes we had done by that time, and how could we work that into a story? So black holes, of course, once they became part of the popular culture, once that idea was introduced to the public at large, clearly, like Einstein's relativity, one of the appeals is the strangeness of it. Einstein was kind of the first science rock star. Unlike many other famous scientists before him, none of them had really achieved celebrity status, even though many of them had done extraordinary work. Well, Einstein came up with this new theory of the universe that was confirmed in an extraordinarily dramatic way in 1919 by an expedition to observe an eclipse of the sun, where by looking at the stars that appear when the sun is covered by the moon, you could see, oh, wait a minute, that star is not quite where it should be. According to the star charts, the light was bent. It was deflected by the gravity of the sun, by just the amount that this fellow Einstein predicted. And then, of course, the popular press tried to wrap their heads around not just special relativity, which by comparison is very straightforward, but general relativity, which is truly a mind-bending and gravitational and space-time bending way of looking at the universe that nobody had ever conceived of before. And the fascination with that extraordinarily challenging set of ideas that Einstein created in his general theory of relativity, I think is a big part of what launched him into celebrity, you know, plus his personality. You know, it was the end of the First World War and people were trying to mend some fences, and, you know, all of these things came together. But I think it's a truism that the stranger a result in science is, from our sort of common everyday perspective, the more attractive it will be to the public, and therefore to the people in television science fiction like me who want to try to find those strange ideas that nobody has ever talked about before, that have that sense of wow, that's crazy, is that really true? And Star Trek, going back to the original series, which I was much too young to work on, back in the 1960s, in their first season, which was in 1966-67, the Enterprise had an encounter with what they called a black star. The term black hole was not really in currency until 67, 68, when a guy named John Wheeler, he says he didn't actually come up with the term, that he heard it from some place, but he was credited with the guy as the guy who made it popular. But at any rate, the black star that the original series Enterprise encountered was a black hole. And the reason that Enterprise didn't get swallowed up is because, of course, our starships have warp drive. They can travel faster than the speed of light. So a black hole is not necessarily a trap for a starship that has this fictional warp drive capability. But it did have the unintended effect of throwing the Enterprise back in time several hundred years, which I don't know if this was something that the writer of that episode was aware of. It's kind of astonishing if she didn't have some familiarity with this idea and predicted it, but there are some ways in which one could imagine a black hole, and maybe Leonard and Alex could talk about this, being used as a time machine for traveling into the past. So that was probably the first encounter on television in a fictional series like Star Trek with a black hole, and we've gone on in the other spin-offs to, you know, explore black holes in lots of different episodes. There was an episode of Voyager called Parallax that was a somewhat fanciful. The Voyager got caught inside a black hole and didn't realize that they were in a black hole until much later in the story, which was kind of fun, raising the question of whether or not the universe we live in is maybe a black hole and we're just inside the event horizon and don't know it, and couldn't know it because there's no observation that we know how to make yet that would confirm or deny that idea. We also suggested in a few episodes, I think, when we brought back the Romulans on Star Trek The Next Generation, and I think we saw them in some of the other shows a little bit, that some of their most advanced warbirds, their battleships, were actually powered by rotating black holes. And I think it was a fellow that Leonard mentioned, Roger Penrose, who recognized a while back that you could conceivably extract energy from a rotating black hole. Whether or not that will ever be a practical power source for a starship or anything else is an open question, the answer to which is very probably no. But we like those kind of extreme ideas on Star Trek, and so we're more than happy to explore them. The problem on Star Trek, and pretty much any TV show, is that you only have so much time to kind of quote-unquote explain an idea from science to your audience. Explanations, or what writers call exposition, are something that every screenwriter in Screenwriting 101 is taught to avoid to the greatest extent possible. So stopping a scene between various characters in our show to explain how a rotating black hole could conceivably be used as a source of energy was not really an option for the writers on the show. So we just had to kind of tell it to the audience as a given, and then, you know, you can go off and look up online or wherever whether or not such a thing is possible. But, you know, I think the good thing about a show like Star Trek is you can get interesting ideas like that out to a wider audience and hopefully encourage people to become more interested in the properties of things like black holes. And then novelists, you know, as Rob mentioned, Paul Anderson wrote this wonderful novel, Gateway. You know, in print, certainly in science fiction, you have a lot more latitude for getting into the details of some of these ideas, and writers like Paul Anderson and course, Robert Heinlein and Arthur Clarke were extraordinarily gifted at bringing those kinds of hard science ideas to the general public. And I think that that only, encourages more interest in the subject and hopefully more support for scientists who want to, continue to study these things.
All right. Excellent. So now I would like to ask the panel a question and then also give the panel a chance to to react to each other. But the one thing we haven't mentioned, which is my favorite sort of idea about black holes and maybe useful in science fiction, is spaghettification. My students love black holes and spaghettification. So if anybody wants to talk a little bit about spaghettification, I would encourage you to do that. Who would like to take that?
Works best with a picture, doesn't it?
Yeah.
Well, when, gravity, you just think of regular gravity, don't even in a way need general relativity, that the attraction of some bit of matter on you is a function of its distance. And so if you're farther away, you have less attraction than if you're closer. And you can imagine that if the attraction is extremely strong, then there'll be a greater tug on your feet than there are on your head if you're, say, falling in toward an object, which I don't know if I don't know if Stephen Hawking was responsible for. I know that in the brief history of time, I think there was an illustration like that, but it will pull you apart, right? Because you have a stronger force here of gravity, a weaker force on your head. Because if gravity is decreasing so quickly that between your head and your toes, the force is different, it's pulling stronger on your feet than on your head, it will pull you into a piece of spaghetti. And so, in a nutshell, excuse the pun, that's the that's what that is.
Although I think the more massive a black hole is, the more gentle that slope of gravity will be. So you could imagine a black hole that would actually be beneficial to chiropractors. I can see a situation where my spine is finally straightened out by the right kind of gravitational gradient to just sort of, give me that little lift that I need in my neck.
Yeah, in fact, I tell my students that if they want to go close to a black hole and study it for their PhD thesis, that they should choose wisely. Choose one of these supermassive black holes outside of which you don't get torn apart versus a stellar mass black hole outside of which you do get torn apart. So in some sense, the little guys are more dangerous than the big guys.
One thing that's interesting is that if you are falling into a black hole, apart from whether or not you're torn apart, it's not like a big alarm goes off. I've gone through the event horizon or through the surface of the black hole. You don't even notice as you're going in. And in fact, these supermassive black holes are so big that you could have a bit of a ride and maybe enjoy it a little bit before you finally get destroyed at the center. And I think even in terms of their density, they're, I think, like the order of density of water or something. So actually it could seem, fairly normal, except you'll never get out and you will eventually get crushed to death.
I'm told it's a once-in-a-lifetime experience.
Yes.
Yeah. So do the panel members have something they want to react to in what they've heard from other panel members? Any comments, thoughts? Andre?
One little thing that we didn't quite, that we just sort of brushed on when Rob was talking about the Poul Anderson novel, there was a book, I forget who wrote it, it was a popular science book, maybe one of you guys remembers, it was called Frozen Star. Does that ring a bell?
George Greenstein.
George Greenstein, very good. And one of the points he was making in that book is that your perception of what goes on near the event horizon of a black hole is going to be a function of your status as an observer. So if you're far outside a black hole and you're watching some poor schmuck spiral closer and closer to investigate, the black hole, getting close to the event horizon, as you watch that person get closer and closer to the event horizon, they seem to be moving slower and slower and slower. And from a distance away from the black hole, you will not actually see that unfortunate astronaut cross the event horizon because time is moving at a slower rate, at least, you perceive his clock moving much, 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 much slower, to the point where it basically stops when he reaches that event horizon. And that's why some people were calling black holes frozen stars. So maybe one of the physicists here who knows much more about this stuff than me can talk to that a little bit, and the strange aspects of general relativity that crop up when you're observing black holes.
I have nothing profound to say, but you mentioned that in the first Star Trek episode where black holes were introduced, the term used was black star. Mm-hmm. And I had a little thing twick in my head that solved a problem that's been bothering me for 30 years when you said that. Because in Star Trek the Motion Picture, if you remember that, yes. Commodore Decker, or Captain Decker, excuse me, says to Admiral Kirk that Voyager had fallen into what used to be called a black hole. And I always, when I watch the film, say, well, what do you call them now? And the answer is a black star. That's the obviously correct terminology in the future. So a little bit of a solution to a Star Trek problem today.
This business of the time slowing down, that's a relativistic phenomenon known as time dilation. And it's just that the time dilation becomes infinite at the boundary or the event horizon of a black hole. So indeed, you actually don't see anything fall through. In case this concept sounds weird, that the passage of time depends on where you are in a gravitational field, there's actually a very nice terrestrial example. Your GPS system in your car works only because the physicists and engineers who designed and built GPS took this into account. The GPS satellites flying around up there are in a weaker gravitational field than we are down here on Earth's surface. And so, in fact, their clocks run a little tiny bit faster than our clocks do. And if this had not been taken into account, then your GPS would not work, in fact. Mm-hmm. It's the only, to my knowledge, current practical application in our everyday lives of the general theory of relativity. That's not to say the theory isn't interesting and wonderful. It is, you know, Leonard and I and others study it, but that's one practical application.
And that's because the way those systems work is by sending, you know, radio signals that travel at the speed of light. So if you're timing things and you might be off, you're only off by a smidgen, let's say, to use a technical term, in your clock, but light does travel an appreciable distance so that you make an error. And the other thing I wanted to say was in general relativity, or in special relativity, the clocks, the time that passes for you, for any observer, is a function of that observer, of where you are and how you're moving. And that's why, so the person who's going into the black hole doesn't notice any abnormality in time, but the person far away, looking at that person, sees that person seem to stop and freeze forever outside the black hole and never really fall in.
And yet the person going toward the event horizon, when they're looking out at the universe, the person going toward the event horizon, when they're looking out at the universe, they're going to see the universe moving, evolving at a much more rapid pace. Is that correct? I mean, if they were to look back out.
Is you can use this to create a time. Actually, it's easy to make a time machine, relatively easy to go forward in time. And so you can do this if you go near the event horizon and you sit there for a while and everyone else sees your time slowing down, and then you manage to get out and come back, much more time will have passed for everybody outside than it has for you. So you might perceive this trip as taking a year or something, and it could be 1,000 years for those back on Earth. So if you want to go forward in time, that's fairly easy. I mean, actually, you don't even have to do that. You can just go really fast and then turn around and come back. You don't need a black hole, and you can get a similar or analogous effect. So I always say time machines are not that hard if you want to go forward in time, which I would love to do because I'd like to know if string theory is correct. And so I think it'll be about 500 years I'd need to go forward to find out. Some have said decades, but I think that's wrong. But anyway, what do I know?
The trouble is you then can't come back and tell your family and friends. You're stuck in the future forever.
And
but eventually your descendants will know that you were right.
Yeah. By the way, since Rob was mentioning novels, a novel that takes really good advantage of that is called World Out of Time by Larry Niven. Very much a novel in which exactly what you prescribe as a time machine is actually used by the protagonist. World Out of Time by Larry Niven. All right, so I'm going to ask the volunteer who's helping us with questions to come up and grab one of these microphones. And now I'm going to encourage people in the room to get involved. What we ask you is if you ask a question, please use the microphone by speaking directly into it so we can record your question for the DVD that they're making. All right, first question over here.
Hi, my question is, my understanding is that black holes eventually evaporate, and I do not understand how that works.
Black hole evaporation. Who wants to take it?
I guess that'll come to me because I've worked with the person who thought up that idea. And here's the thing, I think everything we've said so far, unless I'm forgetting something, is what's based on what's called classical general relativity, which is, general relativity. But general relativity is not a quantum theory. People think of quantum theory as a theory, but it's not really a theory. A quantum theory is a class of theory, a type of theory. And we have quantum theories of this, quantum theories of that. And what we haven't been able to do is get a quantum theory of gravity. So gravity does not obey quantum principles. So what Stephen Hawking did was since we don't have a quantum theory of gravity, physicists have this way of, I don't know, hand waving or I don't know what you would call it, but taking bits of this and bits of that and making arguments. And so he took some ideas from quantum theory and general relativity, and he argued that, in space, from what seems to be nothingness, pairs of particles are always coming into existence and then going out of existence again. Okay, so this just happens everywhere. It's been tested, measured. This is a general feature of what's called quantum field theory, because you can't have a region of space that has absolutely no energy because it's not stable. So it has these fluctuations. And what if you have some of these things happening right outside the event horizon of a black hole? And so one of the particles that comes from nothing falls in, and the other one goes out. And so he's mixed quantum theory and general relativity to analyze what happens with a black hole. And what he found essentially was that a black hole is like what we call a black body in physics. It has a certain temperature, and the ones that are the astronomical size, it's a very low temperature, but it radiates. That black holes actually radiate their mass away. So in a way, everything isn't totally lost in them, but over extremely large periods of time, they will eventually evaporate and radiate away their energy. Now, this is not present and for the foreseeable future observable, but little black holes, it turns out, will evaporate a little. Okay, so if there are, you can imagine having black holes the size of particles, or any size you want if you have the right mass in there. And there were some very speculative reasons that people thought that might actually be created in the LHC, for instance, and it doesn't seem like that's happening. But it does seem like the Higgs has been found, so we should say that, yeah. But they'll announce that next week, and maybe they won't. But they're saying don't say anything about it, right? Maybe for good reason, yeah. So, and maybe I'm really not that close with. So maybe I'm misguided, but I had to throw that in. So anyway, those weren't found. So. Anyway, that's what's called black hole evaporation.
Can I ask just a follow-up to clarify that these virtual particles that are created at the event horizon, at the boundary, they're created everywhere, but some of them, are going to be created right at the event horizon. The particle that falls in, is it correct to say it has negative mass, and that's why the mass of the black hole decreases, or is that a different idea?
Yeah, I don't know. I wouldn't say that, but
why would the
the main idea is that the black hole has a certain temperature,
right,
and that therefore it's radiating energy,
yeah,
and if it's radiating energy, the mass energy, yeah.
But that is, Andre, one way of explaining it, because in relativity, right, it all depends on your frame of reference, and from the frame of reference of the outside observer, it does kind of look like the particles going in have a negative mass, regardless of whether the particle or the antiparticle goes in. And so that actually that is one way of explaining why the mass m of the black hole is decreasing, because from our perspective as outside observers, the particles that are going in are going in with negative mass. That's the explanation I give to my introductory astronomy class, actually. So, and you might say that sounds kind of hokey, but there are all kinds of things in relativity that depend on your frame of reference. So, in fact, it's not that strange a concept once you have seen several examples in relativity of things depending very much on your frame of reference.
All right, next question. Who's got the microphone?
My name is Andrew Masika. My question is, gamma ray bursts, are they associated with black holes? And if they are, what is that association or connection?
Yeah, so gamma ray bursts, unfortunately for Hawking, are not the bursts of gamma rays that are predicted to occur when a microscopic black hole, like the one that Leonard was talking about, evaporates at the end of its life. The evaporation, by the way, increases as the evaporation rate increases as the mass of the black hole decreases, and so you get this explosion at the very end. So there was some hope that gamma ray bursts might be these bursts of gamma rays that are signaling the evaporation of microscopic black holes. It now looks like gamma ray bursts are caused by either a massive star collapsing at the end of its life to form a black hole. Those are the so-called long-duration gamma ray bursts. And then there are the short gamma ray bursts, and they might be either two neutron stars that spiral together to form a black hole, or a neutron star that spirals into an existing black hole, forming an even bigger black hole. So I like to say that gamma ray bursts are the birth cries of black holes in most cases.
Excuse me. I heard over here a comment that said density and black hole, and you said density was roughly the equal of water. And would you clarify that, or did I misunderstand, or what?
Well, if you look at the mass of the black hole and the diameter of the black hole, then you can get an effective density.
Diameter is
I'm sorry, the density is amount, yeah, is mass over volume.
So relative to the event
Right.
horizon, you're defining that as the diameter.
Yeah. In fact,
Singularity.
all the mass is in the singularity, but you can't see that from the outside. All you know is that the mass is within the event horizon. So if you just say, suppose the mass were uniformly distributed, then the average density would be such and such. And in fact, it's easy to show that it's proportional to 1 over the square of the mass. So for the supermassive black holes, the density is actually quite low, the average density, keeping in mind that really all the stuff is in the singularity in the middle. Okay.
Yeah, and that's, again, and the singularity is probably not really there, but that's, the singularity is a function of classical general relativity. When you put quantum theory in, the thought is that will smooth it out.
Right,
yeah.
But it'll just become,
tiny,
a non-zero size, but still microscopically small. But that avoids then the complication of an infinite density, right? If you had a point mass and if you have a point mass of non-zero mass, then you have an infinite density, and that's a problem. But if that thing is not quite a point, then you just have a very high density, but at least it's not infinite.
Yeah, because physicists don't like infinities, and at least as things that would be physical quantities. You can have them in intermediate steps and then wave your hands and get rid of them.
So if that was too dense for us, let's go on to the next question.
It seems like I remember hearing about the time that people first started talking about black holes, that the mass that collapses to form the black hole might reappear at a different time in a different place, or perhaps even in a different universe. But I haven't heard that lately. Is there any chance of that? At the time, it sounded so trippy. Of course, it was 1970 something.
That there was going to be a white hole at the end of the black hole. There was a lot of science. There was a lot of science fiction written on that theme before kind of wormholes became the popular method of doing this. There was a lot of notion that a black hole was paired somewhere else with a white hole, and that what went in had to come out somewhere else. There certainly was. You're right that there was a lot of talk about that.
Yeah, that talk comes from the following. If you look at the mathematics of an idealized black hole, just not considering various complications like the fact that they come from real stars collapsing and stuff, if you include that, it becomes much more messy. But if you look at an idealized black hole, it does look like there's this passageway to another universe or to some other part of our universe. And formally, that's known as an Einstein-Rosen bridge, more informally as a wormhole. And then when you look at it more carefully, it turns out that a non-rotating black hole has a wormhole that only exists for an instantaneous point of time. And in fact, you can't travel through it. It would require travel faster than the speed of light. So the stationary, the non-rotating black holes that's just not a possibility. For a rotating black hole, it turns out the geometry ends up being different, and indeed, these wormholes mathematically look like they exist. The problem is that if you actually start dropping real material into a rotating, or, by the way, a charged black hole, nasty things happen. Either the wormhole squeezes shut, or near what's called, or at the point that's called the inner event horizon, you get this instability that inflates the amount of radiation, and you basically get fried. And so it looks like you cannot actually travel through a wormhole to another universe or to another part of our universe. But the idea in science fiction was based on things that are not quite so crazy. The mathematics, at least of idealized cases, does suggest that.
7 seasons of Deep Space Nine were just shot to hell. Thank you.
You know, speaking of media stuff that Andre just brought up, we didn't mention The Black Hole, which is the Walt Disney film called The Black Hole. And I just want to say it's a terrible film in every possible way, and certainly in terms of the science. So learn nothing about black holes from watching The Black Hole.
So can I follow up on that for 1 second? So when the story's told a lot that when Carl Sagan needed a transportation system for the movie Contact,
right,
he called Kip Thorne and asked, could your graduate students please devise a way to keep a wormhole open long enough for Ellie Arroway to go through it? So are you reporting that that, in fact, is not a workable?
Well, it might be workable. And what Kip Thorne and his students thought up was the possibility that if you had some form of what's called exotic matter, then it could hold the throat of the wormhole open and not have it squeezed shut by the very object that's trying to traverse it, okay? This exotic matter has sort of an anti-gravity, and one way you can get that is by having a substance which has what's called a negative pressure, and in general relativity, negative pressure actually causes a repulsive effect. And indeed, the dark energy that appears to be accelerating the expansion of the universe is doing so, we think, precisely because it has a negative pressure. The problem is we don't know of any way to harness dark energy, and it may well be a property of space itself and thus never harnessable. But Thorne and his students said if there were harnessable exotic matter, that might be a way to keep the throat open. Although more recent work relating to this so-called mass inflation instability that I mentioned suggests that even if the throat were open, you would get fried by all the radiation trapped within the inner event horizon of a rotating black hole.
Oh, those are just engineering details.
Yeah, that's right. But to his
That's what they said about the Wright Brothers in 1900.
Yeah. Well, to his credit, Sagan did try to make Contact as realistic as possible at the time, and he did ask Thorne to try to help him in this regard.
And I will add that we invented the fictional particle Verteron to keep the Deep Space Nine wormhole stable, which had negative mass properties and all these other things. But to acknowledge that yes, this is no simple task to. The aliens, well, that's right, but they through their technology. We didn't do it.
It's why the Cardassians actually have all those ridges everywhere. It's to keep them from being spaghettified.
If time stops before you enter an event horizon, explain please the paradox of how it is the gamma ray burst can be created by a black hole or a neutron star falling in, and why if we look at an accretion disk, we don't just sort of see a pile-up or a train wreck or something instead of...
So the environments of black holes can be incredibly bright. It's only if you're inside the event horizon can you not get out and can light not get out. But when you're dropping stuff in a gravitational field, it's picking up a lot of kinetic energy, okay, from the gravitational energy. And if it's colliding with a lot of other stuff, that bulk energy of motion can be liberated as light. And stuff enters the black hole, but from its own perspective, actually, by the way, stuff does fall in. It's only from the perspective of the outside observer that stuff doesn't fall in. But stuff in the process of falling in is gaining all this energy, and this accretion disk becomes really, really hot. In the case of the supermassive black holes in the middles of galaxies, that's the phenomenon that's thought to lead to this thing that we call quasars. Or in the case of a massive star collapsing, a lot of particles get heavily energized outside the event horizon of the black hole, and so they glow, and in fact they also go along a preferred axis. The axis of rotation of this rotating star has a much smaller density of material than the equatorial plane, and so stuff is trying to get out because it's moving really, really fast, and it tends to come out along the axis of rotation. That forms these two highly collimated jets, and if we're along the line of sight toward either of the two, then we see a bright flash. And if we're not along the line of sight, then we see a more or less normal supernova, because the core collapses but the outer parts explode. So it's a special type of exploding star where the core forms a black hole rather than a neutron star.
Hello. I was wondering if you could talk a little bit about the difference between the formation of a stellar mass black hole and a supermassive black hole, and how do they get so big?
Okay. Do you want me to do that one, or Leonard? Or
Who would like to do it?
I'll take a crack at that one.
Wait, the science fiction guy?
Leonard, go ahead.
The black holes at the center of the galaxies are, I think, believed to have been formed from first formed from very large stars in the early universe, and then gain mass by sucking in other stars over their lifetime. Does that sound?
Yeah, either that or a lot of gas collapses to begin with in a galaxy, and then forms a black hole, and then that black hole sucks in additional material. It's actually a leading cutting-edge question in research right now. Exactly how do the supermassive black holes and galaxies form and evolve with time? So we're not really sure. Yeah, but that could be one way, or it could all just go kawunk, but we're not sure.
So really every black hole should have a sign that says "Do not feed the black hole,"
do not feed
because
the
they
black
get
hole,
bigger,
right?
Yeah. Okay, who's next with a question? Where's the microphone? We have one over here.
Just as a conceptual question, what would happen in the case of a star going around a black hole if a Kepler kind of situation happened where a black hole passed in front of it in our line of sight?
Yeah, what would actually happen is that star would become much, much brighter than it used to be, rather than fainter, as in the case of the Kepler transits. And that's because the black hole would gravitationally lens the light that would have missed you, right? The light that's going out in all sorts of other directions gets gravitationally lensed toward you, and the star actually brightens when it's behind the black hole. And that effect has been seen. It's called gravitational microlensing, but it's been seen in the case of astronomers trying to find hypothetical machos, massive compact halo objects in the halo of our galaxy. When they pass between us and a more distant star, that star is seen to brighten. And that effect has actually been seen. Or when two stars exactly become collinear with you, the observer, the more distant star brightens. So, that effect has been seen.
It's because mass bends light rays, so it can act like a lens for light. And it can bend light rays going around it, and then you get more reach you. And this is how, general relativity was first confirmed, although I think it wasn't really a valid confirmation, but it was seeing the light rays bend around the sun during the eclipse.
So the gentleman with the green shirt, if we can pass over the...
I'm not quite sure how to ask this. But I've read that it's possible that black holes can merge, and if you're talking about supermassive black holes, it's possible that at some point in the past, two other black holes merged to make them that way. But on the time dilation question, from the viewpoint of an outside observer, if nothing ever actually crosses the event horizon, but the two black holes merge at a point in time, excuse me, after they merge, there's one event horizon. So how does the time dilation work? It seems like in that case, the two black holes had to merge their event horizons, so something did have to happen. Ask that okay?
You want to do it or Okay, so I don't want to hog the microphone here. The merging of two black holes eventually creates a bigger event horizon. But it turns out that a lot of energy can be radiated during the merging process, and it goes out in the form of what's called gravitational waves, okay? They go, you know, kind of, they're ripples in the actual shape of space-time. And physicists are now trying to detect these ripples. Probably they'll be detected more likely in the case of merging stars than merging supermassive black holes, but there's a good chance, I think, in the next 5 to 10 years that they'll be detected. Now, you know, during the merging process, the event horizon actually looks quite complicated and stuff, and you can numerically simulate these things. However, once the gravitational waves have been radiated away and the thing is in equilibrium again, then the event horizon basically is a nice sphere. But during the merging process, yeah, it's some weird dumbbell-shaped thing, and you would see infinite time dilation for an object regardless of where it is on this weirdly shaped event horizon. I'm not sure that's what your question was, but I kind of guessed.
And the instrument that is built to observe that is called LIGO. You may have heard of that. The calculations are extremely complex and are done on supercomputers. But what we generally talk about, and when we talk about black holes, are black holes that have gone through all their dynamical changes and they're just sitting there. But when they're colliding, it gets a lot more complicated.
Just one little bit of self-promotion on that. There was an episode of Star Trek Voyager where the writer called me to say, oh, I'm writing this episode, and you know, it's about these aliens, and they're kind of doing an experiment on us, but while that's happening, I want Voyager to be investigating some interesting space phenomenon that we've not seen before. What do you got? And I said, oh, how about a binary pulsar system? Wouldn't Janeway, who is an astrophysicist, by the way, the captain of Voyager, would be very interested if she found a pair of pulsars orbiting a common point in space, especially if they were spiraling in toward each other and about to merge into potentially a black hole. So I said, let's do that. And she said, great, so how would that happen? And I said, let me call somebody. So I called. I didn't want to, you know, I got lazy. You know, last time I solved a differential equation, I think Ronald Reagan was president. So I didn't want to do any of this stuff on my own. So I called a guy at Caltech named Sri Kulkarni, who was very kind and said, oh yeah, that would be interesting, and blah 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 blah. And he said, I'll get back to you. And he kind of worked out the parameters of how long would it take, how safe a distance would we want our starship to be to observe this, what would the gravitational waves be like, and so on. So we did get to sort of try to put that into an episode, and I hope someday when we detect gravitational waves, people will think kindly on the way that we demonstrated that possibility on the show.
Well, we're coming to the end of our time, and I wanted to give the panelists a chance to make a summary statement of some kind and react to some of the discussion. So I wonder who would like to do that first? And
mine will be brief.
Okay.
Black holes are out of sight.
I love black holes. The fact that we're not 100% sure that they actually exist saddens me. It saddens me more than a lot of other things we're not 100% sure that they actually exist, like extraterrestrial life. Because the black hole, in terms of the magnificence of nature, the wonders of the universe, it's hard to imagine anything more mind-boggling than the singularity of a black hole. And I truly and fervently hope that they actually do exist.
I guess I would like to conclude by saying if you're interested in learning more about them, Kip Thorne, who we mentioned earlier, has really wrote a great book called Black Holes and Time Warps, isn't it? Is that, anyway, if you look under Kip Thorne, you'll find the book, and that's a nice book about black holes, the properties, general relativity, and some of the history as well.
Another movie to avoid, in addition to Disney's The Black Hole, it's called Event Horizon.
Oh, yeah, yeah.
Came out, I think, in the late 90s or something. Lawrence Fishburne, who's wonderful and who's a great actor, was unfortunately in this film, and just kind of terrible across the board. And not only that, but really, Stanislaw Lem wrote a wonderful novel called Solaris, which was turned into 2 movies, one in Russia and one here, and they really stole a lot of ideas from Lem's Solaris for this Event Horizon movie and treated those ideas with just kind of a terrible recklessness that I found pretty unforgivable. So it's my last word on black holes.
I can confirm that Thorne's book is very good. Excellent book on black holes. Also, if you happen to be interested, I have a 12-lecture series on black holes called Black Holes Explained. It's sold by the Teaching Company. You can look them up online. It's $40 right now for 12 half-hour lectures.
I'm going to get that.
And there you go. Black Holes Explained. Shameless self-promotion.
Well, let me conclude our discussion then by saying a couple of things. I've been teaching astronomy for a long time, and each quarter when we get to black holes, that's when I have better attendance and more student attention. So look at the audience we have late in the day. So we really appreciate all the interest that you have. We hope, actually, if you would sit down, thank you very much, great. So we appreciate all the interest you have, and I think we should thank the panelists who have managed to convert what is really a mind-boggling concept into an afternoon of joy and delight. So thank you very much.
That's nicely said. A pleasure.
And for those of you who haven't gotten enough science fiction, there's going to be a science fiction panel in this room next.
Yes. Do we have a break?
We do, but only 10 minutes.
It's just 12, 30 minutes. You need to go. Yeah.